Hello everyone, this is our lesson on continuity. It corresponds to 12.2 in Math Excel. That's 12.2 in the study plan and the homework. For more information, you can read 1.3 in the textbook, or I found the OpenStax Calculus textbook PDF posted on Schoology. It's section 2.4. That's a very readable text. So our learning targets today are to determine if a function is continuous at a number, to determine the intervals on which a function is continuous, to become familiar with the conditions of continuity, and to categorize discontinuities as jump, removable, or infinite. So our first activity here, and you can pause the video, is to take a moment and describe each of these graphs and their paths. Think of it, if each one was a road, how would your drives differ? So if we look at each one, the first one up here that looks like an absolute value, if this was a road, it's certainly drivable. You'd have a bend, like a turn, but it's definitely drivable. The one down below here, it's a curvy road, but you could get from one side to the other with no problem. The other two have issues. If you were on this road, you'd never be able to get to this road. And then this road dead ends, and you wouldn't be able to get to this road. And then on this last one, it looks nice and smooth until you get to this hole. It's like a sinkhole in the road, and you can't get over that hole. So if we think of continuity with a casual definition, think of it like this. If you can put your pencil down on a graph and then trace the function without lifting up your pencil, it's continuous. If you have a jump, a hole, a gap, it's not continuous. Formally, a function is continuous if it meets three conditions. First of all, the function has to be defined. So you can't have division by 0, you can't have square root of a negative number. The function is defined for all the values in its domain. Second, the limit as x approaches some value c exists. Both sides go to the same location. So if we're just drawing a function here, if we have our right-sided limit go to this value, a, and our left-sided limit go to this value, b, this would be not continuous. So this condition says that never happens. It never happens that there's a gap. There's no gaps. That's what this condition says. And the third condition says that if there is a limit, that point exists. And this is a tricky one, because if I have a function, let's say this is c and this is f of c, this function, the limit exists as x gets closer and closer to c, because it's getting closer to c on the left side, it's getting closer to c on the right side. For a limit, we don't care what happens at that point. We just care what happens when we get really close to that point. But for it to be continuous, there can be no holes. So I know that even though the limit exists, that point also has to exist. And that's what this condition covers. Now, if you're watching this on video, I'd like you to stop. Go to our Desmos class, and I forgot the code number, but it's on Schoology, and do the continuity activity, and then come back with us here on the video. All right, we're going to look at some different types of graphs, and we're going to determine if they are continuous. So first of all, polynomials. A polynomial is just a string of monomials, which is a number and a variable and an integer exponent. These are functions. You're familiar with the quadratic, the cubic. This one here is a quartic because it's the power of the 4. You can have powers as high as you want. And these are always continuous at every x value, as their domain is all real numbers. So whenever you have a polynomial, notice you can put anything in for your x values. No matter what you put in for your x values, you're going to get a y value, and they're always continuous. There's no jumps, there's no gaps. The limit exists at every point in the domain. The second one that confuses people, which way I put it, is the absolute value function. So remember, the basic absolute value function looks like this. That's just y is the absolute value of x. The one here is a transformation. It drops by 3 and it's stretched by 2. So it's like this. And the reason I include this one is because the unique characteristic about absolute value functions is they have a sharp point. The domain is still all real numbers, or negative infinity to infinity. And there is no value of the domain for which the function is undefined. You can plug in anything for x. And is there any value of the domain for which the limit does not exist? No. So if I pick a point, and as I go from the left, that's the right, and the left, that there's a limit for every point, even this point right here. As my x values come from the right and as my x values come from the left, my function here is going toward -3. And is it true that the limit exists and that the function is defined at that limit? And when your x value is approaching c, the value of your function is f of c. Well, that's true. So, for example, in this case, the limit, let's just say, as x approaches 2, or of my function, which is 2 absolute value of x minus 3, the limit of that is actually 2 times 2 minus 3, or 1. There's no holes. There's nothing that says, oh, at that particular point, our function is defined up here instead. There's no holes. So these functions are continuous at every value in the domain. That is true. And the reason why I included it is because some people get confused at the point. They think it's not continuous. It is definitely continuous. Later on, we will learn it's not differentiable. But that's a couple of sections away. It definitely is continuous. Now we're going to get into our problem functions, the rational functions. Rational functions are not continuous, where there's asymptotes or removable discontinuities. You always have to check to see where the function is undefined. So first case scenario is we know rational functions. They're a fraction. And the problem with the fractions is, where is the denominator 0? So in our case here, in our example, there is going to be a problem where x equals 7. Our question is, well, what kind of problem is it? And that totally depends on whether it's factorable enough. Not. So I'm going to try to factor the numerator. 2x, x, and up top, minus 7 times 3 is 21. If they're both negative, 7 times 2 is 14. Negative 14 minus 3 is minus 17. So it is factorable. If you have a rational function that's factorable, and we want to graph this, I factor it. Notice the x minus 7s cancel. And now graphing this function is as simple as graphing the line, 2x minus 3. So minus 1 minus 2 minus 3. I have a slope of 2. And this is my function. And yes, it looks like a line. Why does it look like a line? Well, because the x minus 7s divide out. However, there's a problem with this right here, and that is when I put in 7, it's undefined. So what I have to do here at 7 is make a hole. So if I try to erase that little bit, it's going to erase my whole line, isn't it? I knew it would. So I have to have a hole right here at 7 because my function is not defined at 7, but it's defined everywhere else. So this one's a hole. So it's not continuous. There is a discontinuity. We call it a hole. And it is at x equals 7. On what interval is the function continuous? It's continuous from negative infinity to 7 and 7 to positive infinity. But notice we use the parentheses because it's not continuous at 7. And that's because when x equals 0, f of x is undefined. We're dividing by 0, which makes it undefined. So that's condition number 1. That's a point discontinuity, or a hole, and that occurs where the denominator is 0, but when you simplify, you can factor out the denominator. Now let's look at condition 2. What if you can't divide out the denominator? Then the rational function will have an asymptote at the x value where the denominator equals 0. And it might also have some other asymptotes too. In fact, this one has 2 asymptotes. Is there a hole or an asymptote? It's an asymptote when x equals 7. So it has an asymptote right here at x equals 7. That means my function, I didn't draw it so good. I kind of hit the function. I shouldn't have. The function is going to get closer and closer to the asymptote, but it's never going to touch it. And notice my function on either side goes in different directions. So not only does there have to be an asymptote, it has to go to negative infinity on one side and positive infinity on the other side. And when that occurs, it's an infinite discontinuity. And then on what interval is my function continuous? Well, again, negative infinity to 7 and 7 to infinity. It is not continuous at 7. We use the parentheses because f of x is undefined at x equals 7. There's another kind of function that gives us discontinuity, and those are the piecewise functions. Now, sometimes piecewise functions are continuous, and sometimes they're not. And you have to look at the transition point. So let's look at the first example. This piecewise function, remember, piecewise function has different function equations for different intervals in my domain. So this one says for all x values less than 1, so 1 is my point where things change, I want to graph the function 3x minus 4. So here's minus 4. If I put in 0, I have minus 4. 1, 2, 3. If I put in 1, I have negative 1. Here is my function when x is less than 1. And it's strictly less than, so I'm going to put a hole here. That hole didn't turn out so well. There we go. And then for the value of 1 and greater, I want to graph the function x squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9. And this one is greater than or equal to, so I use a solid dot here. Notice this one is continuous on the intervals negative infinity to 1 and 1 to positive infinity. However, it has a jump discontinuity at x equals 1. There's a jump. There's a gap. So for all the x values bigger than 1, it's continuous. For all the x values smaller than 1, it's continuous. But it's not continuous at 1. There's a jump discontinuity. Oh, sorry. I answered the questions right there. They should go down there. All right, let's try another one. Let's look at the function x squared minus 5 and negative x squared plus 3. And the point where we're changing over is at negative 2. So x squared minus 5, that's a parabola. 1, 2, 3, 4, 5. Down here at negative 5. But we're only graphing that when x is less than negative 2. So let's put negative 2 in our equation. Negative 2 squared is 4, minus 5 is negative 1. And it's simply less than, so I need to erase that now, and I need to put an open circle. Let's put in negative 3. So negative 3 squared minus 5 is 9 minus 5, or 4. So 3, 1, 2, 3, 4. And if we put in negative 4, 16 minus 5, we're going to jump up to 11. And here's that part of the graph. Now let's do the other side in green. So that's this part right here. Negative x squared plus 3. So negative x squared plus 3, if I put in 0, I'm at plus 3. But this goes from anything greater than negative 2. So let's put in negative 1. Negative 1 squared. And then you negate it and you add 3, gives me 2. So negative 1 gives me 2. And then let's put in negative 2. That's going to be negative 4 plus 3, or negative 1. So at 2, it's negative 1. And my function is going to go something like this. And notice in this case, even though we have a piecewise function, this is continuous. And it's continuous over the interval negative infinity to infinity. Why is it continuous? Well, condition number 1, the function exists for every real number. Number 2, the limits from the left side and the limits for the right side all go to the same point. And the only point really in question is this one here, because we know it's pretty much continuous at every other point. And third of all, there's no hole. While there was a hole there initially from the left side, we filled in that hole with the definition from the right side. So there's no jumps, there's no holes, there's no infinite discontinuities. It's continuous over the whole interval. Now, if you're given a piecewise function and you're asked to find the value that makes the function continuous over all real numbers, you have to look at, I call it like the transition point. So the only problem point here that could exist is at 3. because we know there's this problem right here at 3. So first step, let's see if we can simplify this. Let's see if this factors. So 2x squared. Let's see if it factors and the x minus 3 comes out. So I would have -6 plus 3, which would give me -3 in the middle. So it does. So this is a point discontinuity. So as my x approaches 3, my function is going to approach 3 squared is 9. My function is going to approach 21. But I'm going to have a hole there at 321 because my function is undefined. So if we want it to be continuous, we have to fill up that hole. So in other words, k times, at this point 3, minus 9 has to be 21 to fill in that hole. So I'm going to go ahead and add 9. So 3k equals 30, and my k would have to be 10. So if my k is 10, then this would be continuous. If it's not 10, then the value of the function here would not fill up that hole, would not give us that 21. So this function right here, let's look at this. This would be a parabola. So 2x squared plus 3, 1, 2, 3. It's going to look something like this. But at 3, there's going to be this hole because I have that point discontinuity. And that is going to go on either side. As x gets closer and closer to 3, it's going to go toward this value of 21. So I needed to find the second part of my piecewise function that will fill up that hole, and that's why we chose a k value equal to 10. So here's our formal definitions. F of x is discontinuous at a. If it's discontinuous at a, then let's look at the 3 different discontinuities. The removable discontinuity, that's the hole. At a, if the limit exists, but the function isn't defined, it's discontinuous at a. So that's when the limit exists. So that's something like this, where we have a limit from both sides, but at that particular value, we have a hole. It has a jump discontinuity if the limit from the left side and the limit from the right side both exist, but they don't match up. So from the left, we might be going to one y value, and to the right, we're going to another y value, but there's a gap. There's a jump. It doesn't match. And there's an infinite discontinuity is if from the left side and from the right side, we go to infinity. Now, if you are watching this on video, take a few minutes, turn off the video and go through the practice problems. These are the ones we're going to be doing in class. Then when we do it in class and I have the solutions, I'll post the solutions for you to check later. But these are all the problems that we're going to be working on together in class. And these are due in your notes. The homework is Math Excel. These we're doing in your class. So if you're not in class, please try these problems.